The last time we were introduced to a new aspect to thermodynamics, the so-called entropy, which has the symbol S and is measured in units per degree Kelvin. We also are, of course, familiar with enthalpy, which is measured in joules or kilojoules per mole. Both enthalpy and entropy are important to consider when determining whether a process or a reaction is spontaneous or not. And systems that are entropy favorable will see an increase in entropy because the change of entropy of the universe is larger than 0, which means we have an increase of entropy of the universe over time, which is of course not the case for enthalpy. Enthalpy is always equal to 0 because we can only transfer energy from one form to another, or from the system to the surroundings and the surroundings to the system. However, exothermic reactions and processes that lower the energy of the original and the final state are usually considered favorable. So we have favorable systems that have a negative enthalpy and a positive entropy. So this is the case when both of these aspects are favorable. But that's not always the case in reality. We have processes that are thermodynamically or enthalpy favorable but not entropy favorable, and vice versa. And this is where the temperature comes in, and we can actually control or make a process spontaneous depending on how high or low the temperature is. Of course, there are also the cases where we have a negative entropy and a positive enthalpy, so an endothermic process that also becomes more ordered, and those processes are never spontaneous. So, for example, the rusting of iron is most definitely a spontaneous process, or at least we think so, right? So let's take a look at what we learned last time. We can just look at this chemical equation and count the number of particles on the left, which we have 7, right? 4 plus 3, and the particles on the product sides, we know entropy-wise we have a decrease in entropy, which a more ordered system is not entropy favorable. And so sure enough, we have a negative value for entropy. And if this is a spontaneous process, then we must have a large enthalpy. And that's very true as well here. So this releases a large amount of energy. All that means is that this is an enthalpy-driven reaction because entropy here is not in favor of driving this reaction. So that's the Gibbs free energy equation, right? So if delta G here, Gibbs free energy, is negative, or, if that term is smaller than 0, or basically negative, then we have a spontaneous reaction. And the way this is set up, right, is if we have a negative enthalpy, that contributes to a spontaneous reaction. So any kind of exothermic reaction will contribute to that being negative. And if if entropy is positive, then because of this negative sign, as I said, then we have a spontaneous reaction no matter what. Now, for the scenario of having a positive enthalpy, so this is an endothermic process, and a positive entropy, we can determine, so in order to amplify the entropy test, so no matter what temperature we were, this temperature is not part of the equation here for enthalpy, so if this is positive, we can't increase it or decrease it. But if we have a positive entropy, we can amplify that term by increasing the temperature. So higher temperature will increase entropy, which contributes, because of the negative sign here, which could make up for this positive enthalpy here, right? So we'll revisit that in a minute, but for now, if this is negative, if delta G is negative, we have spontaneous reaction. If delta G is positive, we have a non-spontaneous reaction. And then if it's 0, it's neither or. Okay. So just as a review, a change of enthalpy, a release of energy that's favorable, and if we have to stick energy in, that's non-favorable. And then we have to look at entropy as well. So for these two processes here, we know that burning sugar, producing carbon dioxide, this is not burning sugar, but it's fermentation. It produces ethanol and then carbon dioxide. It's a decomposition. It is both. It has a delta H that is negative, and it has a delta S that is positive. So this is spontaneous, whichever way you want to look at it, right? So we have 1 going to 4. So that's delta S of the system. This is also probably important to point out or highlight every now and then, because if we have a negative change of the system for enthalpy, we have a positive change of the surroundings, and so this can get all kind of mumbled. At least in my brain it gets mumbled, and this is why this is one of my least favorite topics, obviously, entropy, because it's a major struggle for me to communicate that, but I appreciate you hanging with me and sticking it out. So we also know, or you can look at this reaction here, this is entropy favorable, right? The decomposition of water into hydrogen and oxygen gas, which we don't expect to be favorable. And it isn't, because, well, at most temperatures, but we have a delta S that is positive, but we have a delta H that is positive. We have to stick energy in order for that to decompose. So let's take a closer look at these tit for tat or these competition reactions where one is positive and the other one is negative, and vice versa. If we think about water and we think about the two different freezing versus melting, right? That's essentially the same process except the reverse. So if we think about melting, that requires heat input. So that's an endothermic process. So that means this is positive and not favorable. But a heat input also causes a dispersal of energies or particles, which means we have a positive delta T. And so we all know that the freezing temperature of water controls whether this process is spontaneous or not, right? So if you are below 0 degrees, freezing will be spontaneous, and if you're above 0 degrees, melting will be spontaneous, right? So any temperature above 0 degrees Celsius or 273 degrees Kelvin, anything above will make melting spontaneous. So you should be able to, if you have values for delta H and for delta S, be able to calculate the temperature at which point this becomes spontaneous. And so if you look at it, the reverse process, you can do the same thing here, right? Now freezing is releasing of energy, so we have a negative enthalpy, so it would be an enthalpy driven reaction. However, entropy is negative. It becomes more ordered when you freeze. So we want to do those at low temperatures. We want to diminish this term by reducing the temperature. So it's pretty useful to think about that, right? So let's take a look at that equilibrium. So what if we are at exactly at that temperature? Oh, well, I lied. We were looking at a different slide. So as I said, we want this to be negative. So if we have a negative value for delta H, it's spontaneous or enthalpy favorable. And if we have a positive value for delta S, then that becomes favorable. So if I circle all of the instances where we have negative delta H's, so that's enthalpy favorable, and positive delta S's, we can then argue, okay, well, if both of them are in favor, then we have processes that are spontaneous at any temperature. If we have, of course, the opposite here, then it doesn't matter what temperature is. Temperature does not control that. Okay, so the scenario for a thermodynamically favorable reaction that is increasing. Well, it's not increasing in entropy. It's increasing in order, which is what I was going to say, but that means we have a negative value for delta S. We want to do this at low temperature because we are diminishing that aspect of entropy which is working against us, right? So if we have a negative delta S, it's working against us. And of course, if we have the opposite scenario here, we want to amplify the entropy. So we want to have high temperatures here, right? Because this cannot be controlled. It is what it is at any temperature. It's endothermic. It requires energy input. So to make a non-spontaneous reaction at some temperature spontaneous, you run it at higher temperature. So this is kind of like thinking about it logically, right? Of course, we also want to think about this mathematically, right? And so for the melting and freezing of water, you can set delta H equal to T delta S. And so if what we're doing is we're going to set delta G equal to 0. So at this point, we have neither spontaneous nor spontaneous. So we are at equilibrium there. We don't have freezing or melting, which is also what we do in order to determine the temperature, right? We can set delta G equal to 0, use this equation, plug in values for enthalpy and entropy, and solve for S. But in this case, what I'm doing is I'm plugging in the temperature at which we already know we're at equilibrium. So I plug that in, and so those two values are going to be equal, right? So at 273 for melting, both of those are positive 6.01 kilojoules. And for freezing, we're going to also have both of them equal to, right? This is negative, and then this is negative, and I believe that goes away. All right, so that's enough. When we come back, I'm going to do some calculations where we solve for T and determine at what point a reaction is spontaneous.